Hello everyone, I'm Li Haojia. Today I will introduce our work. Fast Dynamic Vision, Detection and Tracking Dynamic Objects with Event and Depth Sensing. It contains three parts. First, I would introduce our motivation and then turn to the methodology. Finally, I will show our experiments and results. Okay, at the beginning, I will introduce our motivation. Nowadays, the drone can fly quickly in a non-static environment and perform the navigation task elegantly. But drones have difficulty in avoiding a flying circle or oncoming birds. In cave exploration, it's difficult for drones to avoid suddenly falling rocks. This reduces the robustness of the autonomous drones. So we start to think about how drones can dodge high-speed moving objects in time. To be able to successfully evade, the first thing is to be able to detect high-speed moving objects. We want to explore what the upper limit of drone perception is, and how to detect moving objects quickly. Firstly, the sensor should be fast enough. We turn our attention to a new bionic sensor, the event camera. It outputs the brightness change in pixel level with some advanced features, such as low motion blur, low latency, high dynamic range, and accurate temporal information. Currently, science reported a high-speed obstacle avoidance work in 2020. It's the first work using the event camera to dodge the dynamic objects and achieve good results. But its self-motion composition algorithm doesn't fuse multiple sensor information and doesn't predict the trajectory of moving objects, so it may fail in some challenging situations. Besides, trajectory estimation of the object by monocular camera observation was proposed at the ISER conference in 2016. But due to the lack of the scale information, the convergence progress is slow and may fail when the observation is insufficient. The pipeline of our framework is illustrated as the figure. There are three procedures in this framework: equal motion composition, fast-moving object detection, and object trajectory estimation. Firstly, we implement an advanced motion composition algorithm fusing IMU and depth data to filter out background events generated by equal motion, including rotation and translation during the flight. The mean time image is an average time step map of the events. Each pixel value of the mean time image is the average time step of corresponding events. Following the motion composition step, we detect and locate the region with the largest average time step in the mean time image. This region represents the area with the fastest speed on the image plane. To obtain the region's bounding box, we introduce an iterative Gaussian fitting algorithm for the object detection step. We also present a moving region retrieval to guarantee the bounding box we get is the most accurate one. Next, the moving object's location is tracked with Kalman filter on the 2D plane, and the object is segmented out on the depth map according to the detection result. Then we optimize the trajectory of the object by minimizing reprojection residues. Next, let's turn to the methodology section. due to the event camera's ego motion or self-motion. Both the static background and the moving object will trigger the events at different locations in order. In order to segment objects, events generated by ego motion, in other words, the backgrounds, should be filtered out first. We need to collect information about all events over a period, and we are inspired by the motion composition of leader. We transform events triggering at different time to the initial moment. Then we calculate the average time step in each pixel to get an average time domain map. Due to the ego motion composition, the static background can successfully be projected into one point, and the average time step is close to the middle value. In contrast, the moving object cannot be projected into one point due to its motion component, so the average time step value is higher. We can easily filter the most part of the background. After dynamic obstacle segmentation, the image is composite of moving object and a little background noise. Commonly, the patterns consist of the moving object have a relatively high mean time step. To detect the moving object accurately, we design an iterative Gaussian fitting algorithm. Firstly, initialize the max time steps location as the ROI center. Then compute the image moments and choose the centroid as the next ROI center. Then choose the confidence area as the ROI region. After several iterations, we can get the better result. After detecting the moving object, we need to estimate the 3D trajectory of moving object. We first track the moving object on the event camera plane by Kalman filter. To address the scale ambiguity issue, we segment the object on the depth camera according to the moving object detection results. We project the detection results in event camera to the depth camera and use the histogram to find the front object. Although the 2D position of the object and the depth has been estimated separately, the event camera is faster than the depth camera, so we cannot associate the object depth and the 2D position on the camera plane directly. So we proposed an optimization-based trajectory estimator fusing event observation and depth observation. Due to the most moving object in the air are projectile, so we assume the object is only affected by the gravity. We can describe the trajectory as a projectile motion, and we just need to estimate the initial position and velocity. Afterwards, we minimize the depth and the event residuals to get the trajectory parameters. Finally, we perform several experiments to validate our algorithm. Firstly, we build an autonomous UAV system including the onboard computer, event camera, and depth camera. We record data in a rich textured indoor scenes, flying forward at high speed. We compare our work with flying gas. It can be seen that the result of our multi-sensor fusion method is less blur. Then we let the drone fly forward at about 2 meters per second and throw the ball at about 12 meters per second and the motion capture system to record the ball trajectory and the drawn data. We compare the currently available molecular trajectory prediction methods with our joint optimization method. The green dots are the ground truth of the motion capture, and the blue line is estimated trajectory. As you can see, our method is significantly more accurate. Finally, we apply our algorithm on the real drawn system. We perform plenty of the real obstacle avoidance experiments to validate our algorithm. This is the experiment in the dark environment. In the end, thanks for your listening.